So I'll be presenting some work that was done in the 60s on this system called Meta2 on the compiler. I think, let me just start by having one single word, which is the word compiler, right? Which is, oops, I think we still have some slides trouble. All right, I think we fixed the problem. So let's get back. So as I said, compilers are often this black box, right? So this is a compiler. I think if you have written C code, you run it through GCC or any of the other compilers, and it outputs the object code. But in the early 60s, it was a lot of work trying to write compilers for different machines. There were a lot of different machines being used at the time, different instruction sets. So I think Dewey Valshore, who unfortunately passed away in 2017, came up with a system for helping compiler writers, right? So a compiler, it's a system for producing compilers, essentially, right? So it makes the life of compiler writers easier. And it's amazing in the sense that it's a really simple system that does what it does. But let's not hear it from me. Let's hear it from somebody else who has also read Shore's paper. And this is Alan Kay, famously known for inventing Smalltalk. And you can see what it says about Shore's work. So hopefully we'll go through his amazing DSL in this presentation. And after that, you have a better appreciation of how compilers work. So in visualizing compilers, we often use what is called T diagrams or tombstone diagrams. And here's an example on screen. This is an example of, in the middle, this T shape is the compiler. There's a compiler from C to x86 machine code. At the bottom, you see the word x86 because this compiler is itself in x86. So the left and right are the input and output of the compiler. So on the left, we have, say, the Linux kernel in C. And on the right, we have the Linux kernel compiled into x86 machine code. Right? So this is a T diagram showing a compilation. So the Linux kernel is a rather complicated piece of program. So we'll look at a very simple kind of example compilation, right, involving an infix expression and converting to a stack bytecode. We'll be using a compiler written in Lua. Unfortunately, I will be not able to do the demo on the computer, so we'll have to look at the results on the slides. So if you run it through the compiler, so the input is the one on the left, which is this infix expression. And the output would be this sequence of, think of it as bytecode instructions for a stack-based machine, right? Push operands onto the stack, and then you call the operators, which will pop off the stack and compute the results. So if you take a quick glance, you can see that the two expressions compute the same value at the end, right? That's what compilers do, right? They preserve the meaning of the expressions through this compilation process. Okay, so that's a compiler, right? But let's get one level meta, so to speak, and look at how we would write this compiler, this infix to stack bytecode compiler. So the T diagram on screen now is showing the process of writing this compiler, right? So on the left-hand side, we have the DSL, which is called Meta2. And then at the bottom is the Meta2 compiler, which will produce the Lua compiler, which we used previously. Right. So Meta2 can't really execute, so we need to convert it to a language that can, where we have an interpreter for, right? We have an interpreter for Lua, so we are converting from Meta2 to Lua, and then we can execute that on the Lua interpreter. So in the next moment, we'll look at what this simple, hello world compiler written in Meta2 looks like. So this is the entire compiler. This is written in Meta2 DSL. So I'll just go through quickly the different lines of it. Well, generally you can see that there's a number of equations, right? Left-hand side equal the right-hand side. Left-hand side is the name of that expression. The right-hand side is the definition of that expression. So very standard notation. And there's some begin and end dot syntax and dot end. Generally in Meta2, the symbols that begin with dot or period is the keywords. Right? This was a kind of a trend in the 60s and 70s. Okay, let's go. So the first part is a rule for the numbers, right? So we have numbers like 1, 5, 2, and so on. So there's a special token keyword called dot number, which will match any sequence of digits, right? So that's what the dot number means. And then there's the part after in the parentheses, which is what the compiler should output. So if during the analyzing of the input, you see a number, it should output push, right? The string push, followed by this $sign. So $sign is, again, a special symbol. Again, if you use things like make, you probably have seen $sign as special variables. The $sign special variable refers to the content of what was matched. So if the number 5 was matched by the special keyword dot number, then the $sign would print the number 5, right? So if it encounters a 5, it would output push 5 into the output. So that's what this line does. The next line is to handle the case of parentheses. So if you notice in infix expressions, parenthesized expressions bind the highest, right? Has the highest binding power. So we will take care of this fact. We will take care of this in this rule. And this rule means an expression 3 is either a number or open parens, expression, and close parens. So expression is defined later, actually. The next one is just to take care of the multiplication and divide. Here we actually have to output something because we're actually matching an operator, right? So when we match an operator, we just output the corresponding bytecode. Let's say MUL for multiplication and DIV for division. And here we also see the clean star, right? Because we have the asterisk open parens after EXP3. EXP3 asterisk open parens means we can have 0 or more of the things in the parens, right? 0 or more asterisk followed by an EXP3 or /, which is followed by an EXP3. And at the topmost level, we have the EXPR definition, in which it takes care of the plus and minus, right? Because plus and minus binds the weakest among the operators in this expression language. So it's basically the same structure as the prior line, except now, of course, when we see a plus, we output the bytecode add, and when we see a minus, we output the bytecode subtract sub. So basically, in these 4 lines, we have defined a compiler from this infix expression. Let's look at the example again. The infix expression to output this list of bytecodes, right? So far, so good. So now we will take it up about 3 notches. We'll look at how to write the metacompiler itself. Okay, and this will be the gist of my talk, actually. So now the metacompiler is basically going to take input is going to be Meta2 DSL, the one we just saw, and its output is going to be Lua code, right? Because we're going to implement all our compilers in Lua. That's our choice of implementation language in this demo. So what we're going to start with, describing the metacompiler itself in its own language, which is Meta2, and then run it through itself, which has already been converted to Lua, and it will produce a version of the metacompiler that is in Lua, right? Because we're converting from Meta2 to Lua. And if you look closely in this T diagram, the 2 T's on the right-hand side are exactly the same, which is what I meant by producing its own code, right? We are using some Lua code to produce the same copy of that Lua code, right? Because the 2 of the T's on the right-hand side are exactly the same. So let's look at how will we write this Meta2 to Lua, right? If you recall, we just learned Meta2 right here, right? Meta2 is this syntax, looks something like this. We're going to convert this syntax into Lua code now. This is going to be slightly more complicated than before. We're still going to have the general structure, right? Dot syntax, program, and so on. And there are going to be 6 rules or 6 equations to do this transformation. So we'll go through them one by one. We'll start with the higher. We'll sort of go top down in this explanation, right? Just now I went sort of bottom up, but now we'll go top down, I think, because it's easier. So at the highest level, we have the concept of a program, a Meta2 program or Meta2 source code is going to look like the following definition, right? It's going to start with the string syntax, followed by a special keyword ID, which is something you define, followed by 0 or more rules. So it calls these expression rules. Something equals something that's called a rule. and it's going to be followed by the special string end, right? Which is exactly what we saw in the previous slide. That is what a Meta2 program looks like. Syntax followed by an ID, followed by a bunch of rules, followed by the end keyword, right? So this is how we define that in itself. It's kind of strange, but okay, just bear with me for a second. So what are we going to output, right? So in this case, there are only two parts where output is happening. So in the first line, when we match the dot syntax, we will output some import. Actually, this local run equal require and so forth is like import statement. So in the Lua code, it requires some runtime library functions to do the input handling. So there's a runtime library that's used I think about 50 lines of code, 50 lines of Lua. So this first local underscore run imports that library so that the compiler can use it. So that's that first part. The second part of output is essentially invoking the Lua function that we have defined. So later on, other rules will create Lua functions, and to trigger the whole thing off, we got to call the function, right? So when you call a function, you use the name of the function, which is actually the name of the .id. The .id will match the name of the function, and we put the parentheses after the name of the function. We are going to invoke it, right? So the last output line is going to invoke a function that we are going to define. So that's it for program. Okay, almost 1/6 of the way through. Okay, so rule is fairly simple definition. A rule, as you can imagine, also consists of a left-hand side, right-hand side, right? So there's the left-hand side, which is the ID, such as the word rule. So it's very kind of recursive. So ID is the name of the rule, right? And then there is an equal sign, followed by something called a choice, followed by the semicolon. So rule has basically these four things: the name of the rule, equal sign, something called a choice, which we'll describe later, followed by a semicolon. And what we're going to do in terms of converting this to Lua is a rule will become a function. So it's quite straightforward. A rule will become a function definition, right? So that's why you can see here we write function followed by the name of the ID, which is the name of the rule, followed by parens and so on. So this is, and followed by end. This is actually defining a function in Lua, right? So the rule is just going to be converted to a function. So a fairly natural compilation strategy. All right, let's move one level down. So what is a choice, right? So as I say, a rule consists of choice. What is choice? Choice is going to consist of sequence of alternatives, right? Like number or parentheses, right? Something A or B or C. So this OR operator is handled at this level. So a choice is defined as a sequence followed by 0 or more, the OR symbol, the vertical bar, followed by more sequence. Sequence will come later. And then there's some Lua code. So in the OR, basically there's this global variable switch, which we will use, right? So when one of the elements in the OR returns true, we will pick that choice and exit this checking, right? Because it's A or B or C or D, right? So we're guaranteeing that only one of the choices, one of the alternatives would be matched. So when that alternative is matched, i.e. if switch is true, then we will sort of break out of this chunk of code, because you only want to match one of the alternatives, right? A or B or C or D. Okay. So the next thing we need to look at, and this is just slightly more complex, is the idea of a sequence. A sequence is A followed by B followed by C followed by D, right? Which is a different thing from the OR. OR is A or B or C or D. So this is a sequence, means it must follow one after another, exactly. So what is the thing that's following each other is something called primary. In fact, primary is sort of the key definition here. Most of the work is done in primary. So primary is going to be a primary followed by 0 or more primary expressions. So I wouldn't go through this in too much detail. Of course, if at some point it doesn't continue the sequence, we'll have to do a break. So there's some details handling the matching of the sequence. But let me move to primary, which is the more important definition. So here is where all the special keywords are handled. So this is going to look very strange. So at first when I saw this, it was like, why do we have .id which is the first line, and we have the third line, which is .id in single quotes. So how do I say this? So the .id at the first line represents to you referring to a rule in the body of some other rule, right? Because I could define a rule earlier and refer to it in the body, right? Just like I could define expr and refer to it inside the definition of exp3, if you recall from my earlier example. So that is the first .id. As I said, rules are going to be transformed into functions. So when I refer to a rule in the body of another rule, it means calling that function. So we see this, dollar sign and the parens. That's invoking a function of that particular name. So if that ID was expr, I'm going to call the function expr parens, right? That's calling the function. So that's what the first line means. The third line, which is the string ID, is literally trying to implement looking for a token, right? So in this case, there is some helper function we use called in the runtime library called parse, and parse uses regular expression to match a token that matches the type ID. ID is essentially, look at this, is going to be alphabetical followed by alpha or digits, followed by 0 or more alpha or digits. So there's number and there's string and there's so forth. And yeah, that's pretty much the definition of primary. I think there's some details here which I will leave it to you to read it up later. So too much for me to go through today. But essentially, we define all the special keywords. We define the parentheses. It's also handled here. Parentheses is the part where parentheses, choice, parentheses. So this allows us to do parenthesized expressions. And then we have the, it defines the handling of the star operator, right? The star operator means 0 or more. That is the very last line of this expression. And if you notice, this is recursive because notice we use the word primary inside the definition of the rule primary itself, right? So it's a lot of this recursive definitions going on. And I know this is getting very heavy. So this is the last slide on this. Most of the magic happened on the previous slide. So the last slide is just how do we deal with the curly braces, right? To do the output, and nothing fancy as you can imagine. It's just going to match. It's going to look for a sequence starting with a curly brace, and either you're going to contain a dollar sign, or you're going to contain some string, right? And then you're going to just do io.write, which is a way to write output in Lua, and it's going to look for the closing curly brace, which is the end of the output. And interestingly enough, in this definition, you see like how this rule is going to work, right? Because it's going to match the open curly brace, the string, io.write, right? That is the dot string, and it's going to write output basically. So this is quite straightforward. So this, I think this entire 6 equations of about 26 lines defines the metacompiler, which is taking in Meta2 DSL programs and outputting Lua code. So why is such a metacompiler interesting or useful, right? Why did Dewey Valshaw, invent this in the 1960s? As I said, the idea was to make it easier for people to develop compilers. But if you look at the compiler system he has developed here, it's actually quite simplistic, right? It only has like 3 different kinds of tokens you can define. It's not really defined, you can use, because they're all built in. You can either use IDs, numbers, or strings, right? And today we would think that this is not enough, right? I mean, in a language, you might have lots of different kind of constructions that are not just these 3. So the power of this metacompiler really that we can modify it and add new features, not by changing Lua code, which would be very tedious, but by changing the DSL definition of the metacompiler. So what would this look like? So for example, if you want to add floating point numbers, right? I think technically you can do it with number and some other things, but we could also use regular expressions. So if you have used like any kind of lexer or parser generator, you probably have used regular expression to define tokens in the syntax. So what if you could expose the ability to define regular expressions to the compiler writer so that they can define new classes of tokens that are beyond the 3 that have been predefined in the language itself. So how we do that? It turns out that it involves adding one alternative into primary. Primary is a whole bunch of different alternatives, like 5 or 6. I didn't count them. So you can see all the or, right? Because there are many, many alternatives. So we're going to add one more alternative, which is, so for example, let's say that our regular expression will start with the symbol hex. Okay, so we're going to say this alternative is going to be the string hex. That's why you can see the single quotes. It's going to be followed by a string, so dot string, and the code we're going to output in this case is going to be this local underscore input equals to underscore run dot parse, and here we're going to inject in the string that we just matched earlier, which is using the $sign, right? So instead of hard coding the regular expression, actually notice in the second and third rule, we hard code the regular expression. So instead of hard coding it in the definition, we let the person writing the compiler define it inside the definition of the compiler itself. So what does that look like? So let me just go to the how will you use this? So I'm going to go back to my example at the very beginning, which was using dot number, right? If you recall, I had this number rule, which is defined using the dot number keyword or keyword for the tokens. But that only matches like 5 and 1 and 20. It doesn't match like a 1.5, right? It will fail to match that. So if we want to match something like 1.5, like a floating point number, we could use this instead. So which is the regular expression support that we just added into the metacompiler, which is write hex followed by a string, which will be interpreted as a regular expression. This is a Lua regular expression, so it may look a little bit odd from either regular expressions in Perl or Unix. Anyway, so you just write the regular expression, and that will do it. So that will be able to match, this regular expression matches some digits followed by an optional dot followed by 0 or more digits, which is the regular expression for floating point numbers. So that's all we had to do. So essentially, we added one line to the metacompiler, and now we can use this hex string with the regular expression in all the new compilers you're going to build from now on. Okay, so I think we're running out of time, so I'm going to summarize. You've seen a lot of Meta2 code. Hopefully, that's not been too difficult. Essentially, we saw that the Meta2 compiler, although I couldn't demo it for you, you could try it. I've shared the GitHub link later in the chat, maybe, where you can take its own source code and generate the output, and you can see that the two pieces of code are going to be identical, right? The two things highlighted in orange or in red here are identical code, right? So this compiler actually outputs itself. So that's it from these 26 lines of the DSL we just went through. And largely as a recap, this is some of the key things I mentioned, which was Meta2 is this compiler system written in 1962. At UCLA by Dewey Valshore. It's defined in 6 rules, and it's able to, it's defined in its own language in about 6 rules, or about 26 lines. And of course, it compiles itself, as I showed you from the T diagram. Unfortunately, I couldn't do the demo, but you can try it yourself later, that it compiles itself and produces its own code. And the key thing, the last part we showed was that you could edit the metacompiler by editing the DSL, right? Not by editing the Lua code, which would be very tedious. So we just edited the DSL to add in the support for regular expressions. And I think one very natural question after all this is you can ask, how did we write the first version of this thing? Because if it produces itself, how did we get the original version? And the simple answer is the original version was written by hand. So instead of asking the compiler to compile itself, we compile it in our brain and output the Lua code manually, so-called handwritten. Right? That's how you get the original first version. And after that, you can keep sort of replicating itself in a sense. Yep, so that's all I have for you today.